On September 15, 2017, a spacecraft the size of a school bus plunged into the atmosphere of Saturn at more than 70,000 miles an hour, and for the final 30 seconds of its existence, as its thrusters fought a losing battle against the thickening gas trying to tear it apart, it kept doing exactly what it had been built to do 13 years earlier. It kept measuring. It kept transmitting. Every single instrument still functioning sent its data streaming back across 900 million miles of space, arriving at NASA's Deep Space Network 83 minutes after the spacecraft itself had already been torn apart and vaporized in Saturn's clouds. That final burst of data, gathered in the last living moments of a mission called Cassini, is still being studied today, and buried inside it is a measurement so precise and so strange that it directly contradicts one of the most fundamental theorems in all of planetary physics. Nearly 9 years later, scientists still do not have a complete explanation for it. This is the story of what Cassini actually found in its final seconds, why the answer breaks a rule that has held for every other magnetic planet ever studied, and why this single unresolved measurement is still shaping cutting-edge research happening right now in 2026. To understand why this specific finding matters so much, you first need to understand what Cassini actually was, and just how extraordinary its final act genuinely was. Cassini launched in October of 1997 and arrived at Saturn in 2004, beginning what would become a 13-year mission, one of the most scientifically productive planetary missions in the history of space exploration. It discovered active geysers erupting from the icy moon Enceladus. It revealed lakes of liquid methane on the surface of Titan. It mapped Saturn's rings in extraordinary detail and watched storms rage across the planet's cloud tops for over a decade. By 2017, though, Cassini was running critically low on fuel, and NASA engineers faced a difficult decision. Rather than simply let the spacecraft drift indefinitely, potentially crashing uncontrolled into one of Saturn's icy moons and contaminating a world that might harbor conditions for life, mission planners designed a final, deliberate act, a sequence of orbits threading the narrow, previously unexplored gap between Saturn's cloud tops and the inner edge of its rings, a region no spacecraft had ever dared enter before. They called this final phase the grand finale. Beginning on April 26, 2017, Cassini executed 22 and a half of these increasingly daring orbits, diving repeatedly through a gap roughly 1,500 miles wide, threading a needle between a planet and its rings with a precision that still impresses engineers studying the maneuver today. Each pass brought the spacecraft closer to Saturn than any instrument had ever measured the planet's magnetic field before. And on September 15, 2017, after the 22nd and final close approach, controllers commanded Cassini to point its antenna toward Earth one last time and begin its final fatal descent directly into Saturn's atmosphere. Joe Pateski, a Project Science system engineer working on the mission at NASA's Jet Propulsion Laboratory, described the mood among the team in the mission's final weeks with genuine mixed emotion, calling it bittersweet, while noting that the spacecraft was, in that final act, simply doing what she was built for. The instrument responsible for the discovery this story centers on was Cassini's magnetometer, led throughout the mission by Professor Michelle Dougherty of Imperial College London, one of the world's leading experts on planetary magnetic fields. Long before the grand finale began, Dougherty's team had already noticed something strange about Saturn, a peculiarity that had puzzled scientists since the Pioneer 11 spacecraft first measured the planet's magnetic field back in 1979. Saturn's magnetic field appeared to be aligned almost perfectly with its axis of rotation, showing essentially no detectable tilt at all. This should not have been possible, and understanding exactly why requires understanding the basic physics behind how planets generate magnetic fields in the first place. Every planet in our solar system known to have a substantial internal magnetic field generates that field through a process called a dynamo, essentially a churning ocean of electrically conductive fluid, molten metal in Earth's case, or a strange metallic form of hydrogen deep within gas giants like Saturn and Jupiter, moving and swirling as the planet rotates. That churning motion, combined with the planet's spin, generates electric currents, and those currents in turn generate the magnetic field surrounding the entire planet. Here's the crucial detail, confirmed by decades of theoretical work and observational evidence from every other magnetized planet in the solar system. This dynamo process is expected to produce a magnetic field whose axis is measurably tilted relative to the planet's actual rotation axis. On Earth, that tilt places the magnetic North Pole roughly 11 degrees away from the geographic North Pole, which is why compasses do not point to true north, they point to magnetic north, a location that drifts over time and currently sits somewhere in the Arctic Ocean, distinct from Earth's actual axis of spin. Jupiter shows a similar tilt of roughly 10 degrees between its magnetic and rotational poles. Uranus displays a genuinely extreme tilt of 59 degrees, and Neptune comes in at 47 degrees. Every single one of these planets confirms the same underlying rule. Dynamos generate tilted magnetic fields, and that tilt is not some minor cosmic accident. It is considered mathematically necessary. A rule called Cowling's theorem, one of the foundational principles of magnetohydrodynamics, essentially states that a perfectly symmetric, perfectly aligned magnetic field cannot be sustained by an active dynamo process at all. The asymmetry, the tilt, is not just common among magnetized planets. According to the physics, it is required for the field to exist continuously in the first place. Saturn broke that rule, and as Cassini's grand finale brought the spacecraft closer to the planet than any instrument had ever measured before, the situation did not resolve itself the way scientists had hoped. It got stranger. Speaking to reporters in the summer of 2017, while the grand finale orbits were still actively underway, Doherty described the growing unease within her own research team. The tilt, she explained, seemed to be much smaller than previously estimated. Odd and quite challenging to explain. Her team had genuinely expected that once Cassini finally threaded its way inside the rings, closer to Saturn than any previous mission had ever ventured, some clear, measurable tilt would finally reveal itself, resolving the mystery once and for all. Instead, she stated plainly, "We thought if we got inside the rings, we would somehow see a clear tilt, and we don't see that. Even with the added precision of the grand finale's uniquely close orbits, the mystery only deepened." The final, most precise measurement came from that last burst of data transmitted during Cassini's actual death plunge. On September 15, 2017, the very last moments of the spacecraft's operational life gathered closer to Saturn's actual surface than any of the previous 22 grand finale orbits had managed. When Dougherty's team finished analyzing this complete data set, the results, eventually published in the journal Science, were almost unbelievable in their precision. Saturn's internal magnetic field showed a dipole tilt of less than 0.007 degrees, an angle so small it is more naturally expressed in arcseconds, working out to roughly 25 arcseconds of total deviation. For comparison, that is a level of alignment more than 1,400 times more precise than Jupiter's own 10-degree tilt, and more than 5,000 times more precise than Earth's 11-degree offset. Saturn's magnetic field is not simply somewhat more aligned with its rotation axis than other planets. It is, for all practical measurement purposes, perfectly aligned, a result that stands in direct, flat contradiction to Cowling's theorem, one of the most fundamental, well-established rules in the entire field of planetary magnetism. This is not a minor academic curiosity. It represents a genuine, unresolved crisis for the theoretical framework scientists use to understand how every magnetized planet in the universe actually generates and sustains its own magnetic field. David Stevenson, a planetary scientist at Caltech, who has studied this exact puzzle since long before Cassini's grand finale, proposed one possible explanation as far back as 1980. His theory suggests that deep within Saturn's interior, the magnetic field genuinely does have a tilt, consistent with what dynamo theory demands, but that a stable, electrically conductive layer somewhere between the planet's core and its visible cloud tops effectively screens that tilt out before it can be detected from the outside, smoothing the field into the deceptively perfect alignment Cassini actually measured. Dougherty's own team has suggested something similar, proposing that some aspect of Saturn's deep atmosphere may be masking the planet's true internal magnetic structure from external instruments entirely. But Stevenson himself has been candid about the limitations of his own screening hypothesis, describing it as, at best, only a partial explanation, a theory that has never been definitively confirmed by direct observation, and that still leaves the underlying question genuinely open. Why would Saturn, alone among every magnetized planet in our solar system, develop this specific, extraordinarily effective screening mechanism, while Jupiter, built from remarkably similar material and operating under remarkably similar internal conditions, shows no comparable effect at all, displaying a perfectly ordinary 10-degree tilt exactly where dynamo theory predicts it should be? Nobody currently has a fully satisfying answer to that specific comparison, and it remains one of the most genuinely unresolved puzzles to come directly out of Cassini's final measurements. The practical consequences of this unexplained alignment extend well beyond pure theoretical physics, touching something as seemingly basic as figuring out how long a single day actually lasts on Saturn. For most planets, scientists determine rotation rate by tracking the rotation of the internal magnetic field itself, since that field is generated deep within the planet's interior and should, in principle, rotate in lockstep with the planet's true underlying spin. Because Saturn's magnetic field shows no detectable tilt or asymmetry to track, that entire method simply does not work. Dougherty acknowledged this directly during the grand finale's final weeks, stating plainly that her team had not been able to resolve the length of day at Saturn, adding only that they were still working on it. For years following Cassini's final plunge, the precise length of a Saturn day remained a genuinely open scientific question, an oddly basic fact about our own solar system that nobody could pin down with confidence, all because of this single, stubbornly unexplained magnetic anomaly. That particular thread of the story, remarkably, has actually been resolved just this year, in a development that shows exactly how this kind of scientific mystery eventually gets worked out, like slowly, through patient, continued research long after the original spacecraft has gone silent. In May of 2026, researchers using the James Webb Space Telescope finally solved the decades-old puzzle of Saturn's true rotation rate, discovering that the planet's apparently shifting rotation signal was never actually caused by Saturn's own deep interior rotating inconsistently at all. Instead, the confusing, drifting signal scientists had been tracking for decades turned out to originate from complex processes happening within Saturn's rings themselves, effectively masking the planet's true, stable rotation period behind an entirely separate, unrelated phenomenon. It took nearly 9 years after Cassini's final plunge and an entirely different, more advanced telescope to finally untangle that specific piece of the puzzle. A second, closely related piece of this broader magnetic mystery was also resolved just this year, in April of 2026, through research led by a team including scientists from University College London. This study did not address the internal dynamo-generated magnetic field that Cassini's grand finale had measured with such startling precision. Instead, it examined the outer boundary of Saturn's entire magnetic environment, called the magnetosphere, the vast, invisible bubble the planet's magnetic field carves out in the surrounding space as it interacts with the solar wind streaming outward from the sun. Researchers discovered that this outer magnetosphere is noticeably distorted and uneven, rather than forming the smooth, balanced structure seen around Earth, and they traced the cause to a combination of Saturn's rapid rotation, spinning once roughly every 10.5 hours, combined with an enormous cloud of charged particles that the icy moon Enceladus continuously sheds into Saturn's surrounding space. This distortion, researchers found, consistently shifts a specific magnetic feature called the cusp, the region where field lines bend back toward the planet's poles and allow charged particles to funnel directly into the atmosphere, off to one side, rather than sitting in its expected symmetric position. This finding helped resolve genuine confusion about Saturn's external magnetic environment, but it is worth being precise about exactly what it does and does not explain. It addresses the shape of Saturn's outer magnetosphere. It says nothing about why the planet's much deeper, internally generated dynamo field remains almost perfectly aligned with its rotation axis. The specific measurement Cassini captured in its final seconds, and the piece of this puzzle that remains, to this day, fundamentally unresolved. There is also a second, entirely separate mystery buried in that same final burst of grand finale data, one that has nothing to do with magnetic tilt at all. As Cassini threaded its way through the narrow gap between Saturn and its rings, its instruments detected a previously unknown radiation belt trapped in the empty space between the planet's cloud tops and the inner edge of its innermost ring, a region nobody had ever been able to directly sample before. This radiation belt appears to function like a genuine electric current, and researchers studying the data determined that it is likely sustained by the radioactive decay of free neutrons, tiny subatomic particles that manage to persist just long enough in this specific, narrow region of space to sustain a measurable radiation environment. 1 year after Cassini's final plunge, in an interview reflecting on everything the mission's death dive had revealed, researchers studying this specific belt acknowledged plainly that, despite detecting it clearly, they were no closer to fully understanding exactly how it had formed in the first place. An entirely separate open question, sitting right alongside the magnetic field puzzle in Cassini's final transmission. There was one more genuinely significant finding buried in this same extraordinary dataset, one that helps explain a completely different long-standing mystery about Saturn, even as it raises its own new questions. As Cassini's magnetometer measured the electromagnetic environment during those final close orbits, researchers led by magnetosphere scientist Krishan Khurana at the University of California, Los Angeles, identified an electric current flowing between Saturn and its rings with a strength comparable to roughly 200 large terrestrial power plants combined. An absolutely enormous amount of electrical energy moving through what most scientists had assumed was a largely empty gap. This current, as it turns out, produces measurable heat in the surrounding atmosphere, and Khurana explained that this discovery may finally help resolve one of the longest-standing puzzles about Saturn: why its upper atmosphere, its thermosphere, has always registered as considerably hotter than models based purely on sunlight alone could ever account for. Khurana noted that this same basic mechanism, an electric current generated by a planet's rapid rotation dragging charged material through its own magnetic field, could plausibly apply to Jupiter as well, potentially even helping explain why storms like Jupiter's own Great Red Spot register unexpectedly high temperatures in their surrounding atmosphere. Step back and consider everything contained within that single final transmission, gathered in the last 30 seconds of a spacecraft's 13-year working life, streaming back to Earth even as the vehicle itself was actively disintegrating in Saturn's clouds. A magnetic field so perfectly aligned with the planet's rotation axis that it directly violates one of the foundational theoretical principles of how planetary magnetism is supposed to work at all, a violation that remains, to this day, without a fully confirmed explanation. A previously unknown radiation belt, sustained by a specific nuclear decay process, whose actual formation mechanism nobody has yet fully worked out. And an enormous, previously unmeasured electric current flowing directly between a planet and its own rings, finally offering a partial answer to a decades-old atmospheric temperature mystery, even while opening up entirely new questions about how similar processes might be operating on other giant planets throughout the solar system. This is, in its own way, exactly what makes Cassini's final act so genuinely remarkable. Considerably more remarkable than simply being a dramatic, cinematic ending to a long and successful mission. Engineers designed that final plunge specifically to protect Saturn's potentially habitable moons from any risk of contamination, a responsible, forward-thinking decision made years in advance. But in carrying out that final protective act, threading a gap between a planet and its rings that no spacecraft had ever dared enter, Cassini's instruments happened to be in exactly the right place at exactly the right moment, to capture measurements more precise than anything gathered during the entire preceding 13 years of the mission combined. The spacecraft's death was not simply the end of its usefulness. It was, in a very real sense, its single most scientifically productive moment. A final burst of genuinely history-making data gathered in the last 30 seconds. Anything on board was still capable of measuring anything at all. Nearly 9 years later, in the middle of 2026, some of the mysteries buried in that final transmission have finally been resolved. Saturn's true rotation rate confirmed using the James Webb Space Telescope, the shape of its outer magnetosphere finally explained through the combined effects of its rapid spin and Enceladus's steady stream of charged particles. But the single strangest result Cassini ever measured, a magnetic field so perfectly aligned with its planet's spin that it should not, by the foundational rules of planetary physics, be able to exist at all, remains genuinely unresolved. Somewhere deep within Saturn, according to the leading theory, a hidden layer may be quietly screening the planet's true, properly tilted magnetic field from ever reaching the surface where any spacecraft could actually detect it. Or something more fundamental about how giant planets like Saturn generate their magnetic fields in the first place may simply not yet be understood at all. Cassini is gone. It has been gone for nearly 9 years now, vaporized in Saturn's clouds within seconds of sending home the most precise magnetic measurements any instrument has ever gathered from that planet. And the single strangest thing it ever found, sitting right there in its very last transmission, is still, right now, waiting for an answer nobody has yet been able to fully provide. If you want to know when scientists finally crack the mystery of Saturn's impossible magnetic alignment, subscribe and turn on notifications. Because the data that might eventually solve it is still sitting in an archive, waiting for the next researcher determined enough to take a fresh look at what Cassini left behind.